Do you want to learn about transmission line parameters and performance? Hey everyone, and welcome back to the channel. Today, we're diving into a topic that's fundamental to electrical engineering: transmission lines. Have you ever wondered how electricity travels hundreds of miles from a power plant to your home with minimal loss? The secret lies in understanding the parameters and performance of these incredible power highways. So, if you're ready to unravel the mysteries of transmission lines, you're in the right place. First things first, what exactly are we talking about when we say transmission line parameters? Any transmission line has four key electrical properties that define its behavior. These are resistance, inductance, capacitance, and shunt conductance. Let's break them down one by one. Resistance, which we represent with the letter R, is probably the one you're most familiar with. It's the opposition to the flow of current. In transmission lines, the conductors, usually made of aluminum or copper, have some inherent resistance. This resistance causes power loss in the form of heat, something engineers work very hard to minimize. It depends on the material of the conductor, its length, and its cross-sectional area. Next up is inductance, symbolized by L. Whenever current flows through a conductor, it creates a magnetic field around it. This magnetic field stores energy, and the property that relates the current to this stored magnetic energy is inductance. This effect is significant in AC systems, where the current is constantly changing. It's causing the magnetic field to expand and collapse. This changing field induces a voltage that opposes the change in current, which we call inductive reactance. Then we have capacitance, or CA. Transmission line consists of at least two conductors separated by an insulator, which is usually air. This setup is essentially a giant capacitor. Potential difference or voltage between the conductors causes an electric field to form in the space between them. This electric field stores energy, and capacitance is the measure of this ability. The effective capacitance is more pronounced in longer high voltage lines. Finally, there's shunt conductance. G. This parameter accounts for the leakage current that flows between the conductors through the insulator. In overhead lines, the insulator is mostly air, which is a very good insulator. However, factors like dust, moisture, or imperfect insulators on the towers can create a small leakage path. For most practical overhead lines, this leakage is so tiny that we often neglect it in our calculations to simplify things. But it's good to know it exists. So we have R, L, C, and G. These four parameters are distributed all along the length of the line. They're not just lumped in one spot, they're everywhere. This is why we call them distributed parameters. Now, how do these parameters affect the performance of a transmission line? This is where it gets really interesting. The performance is mainly evaluated by two key metrics: voltage regulation and transmission efficiency. Voltage regulation is a measure of how well the line maintains a constant voltage at the receiving end as the load changes. Ideally, we want the voltage our appliances receive to be stable. However, due to the impedance of the line, primarily its series inductance, the voltage at the receiving end tends to drop when the load increases. Good voltage regulation means this drop is very small. We express it as a percentage, and the lower the percentage, the better the line's performance. Transmission efficiency, on the other hand, tells us how much of the power sent from the power station actually reaches the destination. It's the ratio of the power delivered to the load to the power sent from the source. Where does the rest of the power go? What's lost, mainly, is heat due to the line's resistance. This is the I²R loss you might have heard of. Maximizing efficiency is crucial for both economic and environmental reasons. We want to deliver as much power as possible without wasting it along the way. To analyze performance, engineers classify transmission lines into three categories based on their length and voltage level: short, medium, and long lines. For short lines, typically under 80 kilometers or 50 miles, the effects of capacitance are so small that we can completely ignore them. This makes the analysis much simpler. We only consider the series resistance and inductance. For medium lines, let's say between 80 and 250 kilometers, the capacitance starts to become significant. We can't just ignore it anymore. To simplify the analysis, we often lump the total capacitance and model it as being connected at one or more points along the line. Common models for this are the nominal T or nominal P methods. Finally, for long lines, those over 250 kilometers or 150 miles. The parameters are truly distributed, and we need to use more complex mathematical methods involving hyperbolic functions to get an accurate picture of the line S behavior. Here we can't use the lumped approximations anymore, and that's a comprehensive overview of transmission line parameters and performance. From the four fundamental properties, resistance, inductance, capacitance, and shunt conductance, to the key performance indicators of voltage regulation and efficiency. It's a fascinating field that's essential for our modern world. I hope this video helped you get a clearer understanding of how transmission lines work. If you found it useful, please give it a thumbs up and consider subscribing for more electrical engineering content. If you have any questions, drop them in the comments below. Thanks for watching, and I'll see you in the next one.